Lesson 875, Zero and Negative Exponents, using patterns to understand zero and negative exponents. In this lesson, we'll understand and justify that anything raised to the zero power equals 1, and anything raised to a negative power is equal to 1 over that same base raised to a positive power. And we'll determine if two expressions are equivalent. You're in your notebook on page 124. And I'm assuming you've worked your way through lesson 5 on the Desmos activity. We have two goals. First of all, explain what it means for a number to be raised to and we're actually going to talk about two things today. For a number to be raised to a zero exponent, and for a number to be raised to a negative exponent. That's the main thing that we're trying to do today, but you'll also need to be able to determine if two expressions are equivalent. Let's go ahead and get started. Now, our concept of exponents as repeated multiplication is harder to see. It's less helpful when the exponent is 0 or when the exponent is a negative number. But there's still some patterns that can help us to discover what 0 or negative numbers mean as exponents. So we did this in the activity in class as well. But let's look at this table of information and look for some patterns that we see. The first column shows a base raised to an exponent. And in this whole column, the base never changes. The base is 8. But you can see that the exponent starts at 3 and decreases by 1 each time. 3, 2, 1, 0, -1, -2, -3. So there's a clear pattern with the exponents here. The second column is going to show some repeated multiplication. We'll come back to that in a moment. And this last column shows the value of whatever is in that row. So as we look at that powers of 8 table, how do we know that the numbers change? How do the numbers change as you look down the table from 8 to the third power to 8 to the second power to 8 to the first power? Well, I can see that in this first column, the exponents are decreasing by 1. And in the second and third columns, I'm really dividing by 8 with each change in level. So, for example, 64 divided by 8 gives me 8. 8 divided by 8 gives me 1. 1 divided by 8 gives me 1/8. And all of these, I'm going to continue to divide by 8. And you can see that happening over here. Values are divided by 8 as we look down the table. I want to skip around just a little bit because I'm going to start with what I feel is the easier of the two rules that we're looking at today. The first rule we're looking at is explain what it means for a number to be raised to a zero exponent. So let's focus in on this row. We'll go below that in just a moment. But 8 to the third, 8 to the second, 8 to the first, 8 to the 0 power. And what happens if 8 to the third power is 512, and I keep dividing that by 8 to get to the next power down? Let's look at what happens from 8 to the first power to 8 to the 0th power. If I'm dividing by 8 every time, then I'm going to take 8 to the first power divided by 8, and that gives me 1. And that's going to happen every time as you move from the first power to the 0th power. Let's see if we can jump down here and skip over this for now. So I'm going to say, because 8 to the first power is 8, If I'm dividing by 8 each time, then 8 to the 0th power must be 1. So it's that division that's happening that helps us to understand that anything, it turns out, that's raised to the 0th power is equal to 1. Now, the more difficult rule is the one with negative exponents. So let's look back at these patterns in the table and talk about these negative values. Now, this is going to take a little bit more effort here. I want to show the repeated multiplication that happens here as I look at these two columns. So 1/8, I'm just going to write that right here. That's 1 divided by 8. That's just another way of writing 1 divided by 8. Now, just for right now, I'm going to write 8 to the 1st power because I want to make a connection between this negative exponent and it becoming positive when I put that base in the denominator. Let me come down one more row. 8 to the negative 2nd power, I can show this with repeated multiplication. It's just that these two powers of 8 are going to appear in the denominator. Oops. I think I meant to write 8 to the 2nd. I'll do it over here. So 8 to the negative 2nd power is the same as 1 over 8 to the positive 2nd power. You can see there that negative changed to a positive once we put it in the denominator. So 8 to the 2nd power is, there's the repeated multiplication. Let's do it one more time. 8 to the negative 3rd power is the same as 1 over 8 to the positive 3rd power. And the repeated multiplication would look like 1 over, there's 1, 2, 3. There's that repeated multiplication, and that negative just lets me know that I've moved to the denominator. In fact, I'm going to jot that down as something important about negative exponents. Negative exponents show repeated multiplication in the denominator. Negative exponents show repeated multiplication, just like we have all along, in the denominator. So, based on the patterns in the table, another way to represent 8 to the negative 5th power, let me just write it here, is going to be 1 over 8 to the positive 5th power. In other words, that repeated multiplication just happens in the denominator. There's 8 to the 5th power. 1, 2, 3, 4, 5. Whew. So we're getting there. We're going to do that negative exponent one last time as part of our summary questions down here. What's the relationship between 10 to the 5th power and 10 to the negative 5th power? All right, I'm going to expand both of these out so we can make sure we understand what the negative exponent means. The positive exponent, we've done this a million times. 10 to the 5th power, means 10 times 10 times 10 times 10 times 10. 10 is repeated as a factor 5 times. But when it's a negative exponent, I still have that repeated multiplication, but the repeated multiplication happens in the denominator. So I'm going to write 1 over 1, 2, 3, 4, 5. There's my repeated multiplication in the denominator. So that's the relationship between those two numbers. 10 is repeated as a factor, but here it's repeated in the numerator, and here it's repeated in the denominator. We're going to look at these last three problems, but I'm not going to lie, they're pretty hairy. It's just going to give us a chance to exercise our skills. So, let's try this out. Write each expression as a single power. Well, I'm going to, when in doubt, expand it out. So I'm going to expand these three powers. I'm just going to be really careful about this one. This one's going to change to the denominator. You'll see what I mean in just a moment. So let me expand out this 7 to the 4th power. And when I expand out that 7 to the negative 2nd power, I'm going to show that repeated multiplication in the denominator. There's the 7 to the 2nd power. And then in the denominator, I'll expand that 7 to the 12th out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now that I've got everything expanded out, you know how to cancel things at this point. Let me see if I can find another pen. Of course I can't. So let me just cancel. All of these are canceling to 1. 7 divided by 7 is just 1, 1, 1, 1. So in the numerator, all I'm left with is 1 times 1 times 1 times 1. And in the denominator, I have, let's see, how many powers of 7 do I have left over? 10. Now, technically, this isn't written as a single power. 1 over 7 to the 10th power means that I have 7 factors of 10 in the denominator. And that's what that negative exponent will indicate. Whew. This next one's not so cumbersome. So for this one, I've got repeated multiplication in the denominator. I'm probably going to end up with a negative exponent for my answer. But this is the same as 1 over 5 to the 3rd power, 1 over 5 times 5 times 5. And if I have repeated multiplication in the denominator, I can express that with a negative exponent. Remember that 5 to the negative 3rd power is the same as 1 over 5 to the positive 3rd power.